Hello, in this video we're going to talk about Compiler Toolkit Cudagraphs. So what is Compiler Toolkit? Compiler Toolkit is this new thing we're working on where we give more control to the users when using the compiler. So in practice what this means is you have a model, you export it, and then users define fx graph passes to modify the graph, and then we do the compilation. In practice, at least so far, the three most common passes are the following: bucketing, reordering, and CUDA graphs. And you can visualize what's happening here. So like an fx graph is just like a list of operations, right? So bucketing is when you notice that two operations can be bucketed together. The most common is collective operations, like network operations. And if you bucket them together, then you save on the overhead. So like, for example, instead of doing two network calls, you can do one network call with a much bigger buffer, and you save on the overhead. The second one is reordering, where we're like, oh, we can actually launch this async network operation earlier. So let's move this over here, and let's move this over here. And then the last one is CUDA Graphs, which we will talk about here. So if you think about PyTorch and GPUs, typically what happens is you invoke this Python code, like t.sign. And what that does is it schedules a kernel launch. And a kernel launch has some inherent overhead. So if you call sign 3 times, you're going to incur this overhead 3 times. What CUDA Graphs allows you to do is it allows you to record all of these kernel launches. And as long as you have static memory input addresses, you can replay it without all of the launch overhead. And so this is really, really helpful for certain types of hardware, and generally can speed up your model quite a bit. And the last thing I want to talk about is like how are these passes done? So the bucketing and reordering passes are done at the fx graph level, which means we literally will iterate through the fx graph and do mutations in the fx graph. CUDA graphs, on the other hand, actually operate on the forward. It will basically just wrap the forward in a CUDA graph class, and then it will handle the record and replay. So let's look at the code for how this was added. So one thing you'll notice is there's this end with pass helper, and the reason why is because CUDA Graphs is wrapping the forward, we need the fx graph to be finalized, and so we need to make sure that the CUDA graph is the last pass. If you look at CUDA graph, there's just like a bunch of setup code. We're not going to go too much into the details, but it's things like making sure there are static inputs, handling the copying, handling the warm-up, stuff like that. Here we do the passes to make sure that CUDA graph is the last pass that's applied. And then here's kind of interesting. So the way that we apply the pass is we wrap the forward with this CUDA graph wrapper. Now this is super duper misleading, because you're like, well, why are you only wrapping the forward? It shouldn't be the backwards. And the reason why this also works with backwards is because the backwards is also a graph module, and when you invoke the graph module for backwards, it's actually called forwards. Very confusing, but the basic point is when you're doing your compile, the way the compiler works is that it traces out a joint graph, it partitions it into the forwards and backwards, and then applies the compiler on both. And so in this case, when we apply this CUDA graph wrapper on both the forwards and the backwards via the compiler, it will wrap both in CUDA graphs. So yeah, at a high level, that's kind of how CUDA graph works in the Compiler Toolkit. Hopefully this was helpful, and I'll see you in the next one.